Hello and welcome everyone to our Dr. Data Science for June. I am Ninad Save and we have Stephen Hillian and Colin Gray today presenting for us. As always, our Dr. Data Science happens third Wednesday at 9 a.m. Pacific or 12 p.m. Eastern Time. So next session will be on July 15th and we post every session recording on YouTube. I will post the link for the playlist in chat in a short while. If you have any questions in this session, please post those questions in Q&A section so we can able to answer it properly rather than in chat. Over to you, Stephen.
Great, thanks, Ninad. So as usual, our data science sessions are split between a quick nugget of information at the beginning. Last week, we looked at the method of cross-validation as a way to evaluate models. And then we had a special guest star for our featured session, Peter Shaw, who was retiring from TIBCO. He's now happily enjoying his retirement, and that was on methods of variable selection. It was a fascinating overview of different approaches to reducing the number of variables in a model. And as Ninad said, you can find that on YouTube. It was a really good session, really interesting. This week, I'm going to switch gears a little bit in terms of our nugget of information, although actually both of our topics this week are sort of related to Peter Shaw. The information gain is about a technique, really a sort of a protocol, if you like, that Peter Shaw taught me a few years ago. And then regularization is a drill down into one of the topics that Peter mentioned in his session. We mentioned regularization briefly as a method of reducing variables. And Colin's going to drill down into that in a little bit more detail because it's a widely used technique and can be a little confusing. Okay, so let's start with our information gain. And the question here is, how do you start exploring a new data set? And I think one of the things that people, so you're just presented at the beginning of a project with an entirely new data set, you haven't seen it before, and you want to start approaching the data set in view of some particular business problem, something you want to predict, something you want to interpret, whatever it might be. And I think there are standard things that people tend to do very commonly to use some sort of summary statistics to understand the contents of each column, its distribution, maximum, minimums, number of null values, missing values, that sort of thing, data types. Often people will draw simple charts, often frequency charts and histograms, again, to look at the distribution of data, maybe scatter plots, to understand how the variables interact with each other. All of these are sort of aggregate methods for looking at a data set. And one thing that Peter Shaw always recommended is precisely the opposite approach. It's kind of the opposite of big data, which is look at one record. Just look at a single row of data in the data set. And of course, you might iterate on that and do a few more. But the point is just one at a time, get to know your data, look at each single observation. So I'm thinking back to a project that we worked on a couple of years ago that's been published in the blogs that you see at the bottom there, the TIBCO blogs, that we did with Tipping Point about looking at parking fines in the city of San Francisco. And this was the data set at the top here that we looked at. And just looking at that middle row there, the one with the smaller circles there. So you see, we've got columns here. What was the violation? Where did it happen? How much did they pay? The zip code, the make of the vehicle, and so on. And just looking across on this, one of the things we noticed very quickly was that we have these two columns, total amount due and total paid. And that's just good to see, right? One of the things you want to do is just look at the data, look at the columns that are available to you. And it's not just the amount that was on the ticket, but also how much was actually paid. And we saw quite a few where the total paid was zero. And another thing that was mysterious about this line was that for street cleaning, $192, there is no such ticket in San Francisco. It is a very expensive city, but you don't pay $200 for street cleaning tickets. So that was immediately suspicious to us. We asked questions about that, figured that probably what was going there is that the total amount due represented a fine because of a late payment because they hadn't paid it, as indicated by the other column. One thing we were looking at is locations of where tickets were given out. Was there a bias in the way that tickets were given out or more expensive tickets in certain regions? And we can quickly see here the zip code is not always present in the data. And in fact, looking at some other roads, we found that there were misspellings in street names and so on. And so the location data had to be treated very, very carefully. Another thing that we therefore said was, well, look, if some tickets are much more expensive than others, perhaps because of fees, maybe we can understand whether that's sort of unfairly impacting certain communities, maybe lower income families, low income drivers. But there was no way to tell that from the information. There was no way we can get information on the drivers themselves. But we thought, well, maybe the make of the vehicle is kind of an indicator. Maybe a more lower income driver is unlikely to be driving a Tesla, for example. And in fact, it turns out that there was some sort of signal in the data around that. And then we started looking at those plate numbers. You see those listed in that second circled column. And I was wondering, what is the significance of the numbers in the plate? And we actually realized that there's a correlation between sort of the leading digits in that plate number and the age of the vehicle. And that actually allowed us to start drawing some conclusions around the impact of high value tickets on vehicles that were older and that were likely correlated with lower income drivers. So just getting to know that one row of data really did set the course of the entire investigation. Another quick example, I mentioned about just looking at one observation. Colin, if you can just switch to the next slide. Sometimes that one observation might actually contain multiple rows of data, especially in the case of time series. So here, for example, we've got in the top table a record that indicates when a certain part, a mechanical part, has failed. So the part with ID 89732 failed, you notice, on May 30th. And we've got some time series data beneath that, and I've shown there the rows for 89732. You can see the IDs on the right. And for each date here, which for security reasons I fuzzed out, you can see various sensor readings on that part, on that mechanical part. So maybe by looking at those sensor readings, we can predict when something is going to fail. So just looking at the path of one particular part, just part 89732, allows us to maybe get some ideas about how we might model this. In fact, one of the first things I do is to draw some time series charts on the next slide so that I can actually look into each of those sensor readings. And you see in the lower sensor readings at the bottom there doesn't seem to be anything correlated too much with May 30th. It appears about a third of the way through these charts. But you'll notice those first 4 sensor readings, they sort of leap up around May 30th to a higher level. So one of the ideas that we had was that maybe under average values of the first 4 sensor readings might be an indication that a part was about to fail. And again, that suggestion, and many others like it, of other variables we might look at, just came from looking at one particular part and the observations associated with that particular case. So again, it's sort of the opposite of big data. It's tiny data, just looking at one row at a time to indicate what variables you might want to look at and what's really the contents of your data. Okay, so again, thanks to Peter for that tip. And now we want to talk about the process of regularization, which, as I said, is a commonly used technique, but often a bit confusing, especially for newcomers. So Colin, let us know what you've been thinking about regularization.
Great. Thank you, Stephen. Yeah, so regularization is something that I've started looking at and playing with. I think as data scientists, we often have our favorite models and techniques that we use, and I've certainly been prone to focus on tree-based models more than regression. So I've been doing a project where actually I explored a lot more around regressions, and the topic of regularization came up. So I thought it would be good because, like Stephen said, it can be quite confusing about what it actually means. I think it's quite a strange term, and trying to relate that to data science. So what is it? And it made me think that I don't think the word regularization really helps me understand what it is. And it kind of reminded me of, I mean, you can tell the age of this, but it's an age of me by picking this example. But this picture from The Dwarf, which was an old sci-fi comedy.
Yeah, I thought it looked familiar.
Yeah, it's quite fuzzy from the years gone by. There's a great scene where they're in space and this sort of portal appears and they walk through and it takes them, you know, millions of miles away or possibly through time. And Kat in the middle says, "So what is it?" And the people, Lister and Rimmer on either side of him try and explain it. They explain it in increasingly complicated ways. Space-time continuum, it's a rift and tear in space. And he keeps just going, "So what is it?" And they say, "Well, it's a portal you walk through and you go somewhere else." And he's like, "Well, it's just a magic door. Why didn't you just say that?" And I think with data science, we we often have complex terms that sort of confuse and you maybe even obfuscate how the meaning of things. So I wanted to dig into regularization and see if that term makes a bit more sense, but really, what is it? And
I have to say, Colin, it certainly never made sense to me. I hadn't even thought about that, but you're right. It doesn't suggest anything to me.
Yeah, I mean, I looked it up in Google, and here you have an example, electrical implant to regularize heartbeat. So I'm thinking, let me translate that. Something to regularize my data science model. I still don't know what that means. So let's go through it, and I hope there's a hint of where the word came from by the end. But the important thing for me as a data scientist isn't so much the origin or even the complex mathematics involved sometimes. It's about how can I apply this to make good business production standard data science models. So what is it? In my words, and a lot of great blogs out there, I think would use the same sort of words. I think it covers two things. A method to prevent overfitting. And I think I'll briefly go into what that is, because I mean, that's another data science term, but I think most people will understand that. The other thing it does is it helps reduce model complexity. Model complexity is becoming increasingly important because you may have heard things like model explainability and how you can interpret a model, especially around ethics in data science. It makes models, if we have less complex models, we can explain how they're behaving easier. It also means we can understand the insights and impacts they're having if we have less components that we can adjust and learn from. So I think that has a lot of benefit, and that's why regularization can be really powerful. So let's just cover what overfitting and complexity really is, just to get that sort of set out. I've got this example here. It's just from, you can download it here and run it yourself in Python from the scikit-learn site. And what it does is it plots three simple models, if you like, through this training data. So the blue dots are your samples and the line is your model fit. So what we do is it does a very simple 1 degree. That's a straight line. And you can see it doesn't really fit our data. You know, you would say that's underfitting actually, and it doesn't have good predictive power. The degree 4, actually, it's got a really nice shape. It follows the samples. So actually, I'd be pretty happy with that model. There's a few that are off the line, you know, so it's not perfect, but it looks good to me. And then we up the degrees again, so the model can really become quite complicated. And you can see it does all these sort of really big wide loops, but it fits the actual sample data better than the previous one. But it's doing all sorts of wacky things here. And that's where you would argue, is this model overfitting? So overfitting is where you overtrain your model to predict just your training data. So what does that mean? Well, it means when you try and predict some new data, chances are it's not going to do a good job, and effectively becomes kind of useless as a model if it can't predict the future or unknown data sets, because that's the whole point of your model. So here's a sort of diagram that you often see again. And what is the impact? We measure model error as in how good it can predict. So as your models get more complex, you often see this blue line. That's the performance of the training set in the model. It gets better and better as you get more complex models. But what you find is the test data, the data the model hasn't seen, it will improve for a point, but at some point it starts to get worse. So the predictive power of your model is actually getting worse as your model gets more complex.
Got it.
Yeah, and the danger here is that your R squared or whatever metrics. So Peter covered lots of great different ways to measure how your models work. They might look good here, but again, in real world application, they'll give a much worse answer. So the major impact, again, it's about what's the real life impact. Your overfit model may have little or no predictive power. So it's really important to find that sort of sweet spot there. So regularization to the rescue. How can regularization help prevent that? So this is getting into a little bit of how we rate or rank model performance, and regularization plays a role there. So put it in very simple terms, again, avoiding going into the mathematics at this point. When we assess model performance, we normally just have some function that describes model error. There's lots of famous ones, so I'll put a couple of these here. You've got mean absolute error, you know, so looking at the difference between your predicted and your real values, the absolute difference, and that's sometimes called L1 error or L1 loss. The other very common way is mean square error, where it's taking the square of the differences between predicted and real, and that's often again referred to as L2 loss. So your model performance is described by loss, or sometimes people call it cost as well. It's one of these things where people interchange different terms, but really I think of it as how good is your model. You're measuring it in some way, and you can do that in different ways, and which one is best to use of these is you know, a topic in itself. So okay. So what does regularization do? Well, what it does is it adds an extra component to this score, this performance score. And what it's saying is we'll not only account for our measure of model error or loss, we add a regularization penalty. So we're not altering the models themselves. What we're altering is how we assess which model is best. And that's really key because it has a really fundamental impact when you bring that into something like regression.
So in your last example, it's a little bit like counting how many wiggles there are in your graph. You don't want too wiggly a graph.
Yeah, exactly. So, sorry, I've just gone the wrong way. Oops.
Just hit the back button maybe, Colin.
Yeah, sorry. Says it could only go forward. Yeah, so exactly. That's exactly what we're talking about here. So, yeah, it's trying to prevent and penalize this situation here.
Okay, can you explain a little bit more detail what regularization, what that penalty is then?
Yeah, so exactly. So this is what this slide is trying to do. Now, it's a little bit heavy on, you know, equations, but I wanted to I'll try and talk it through step by step. And this is why I think this topic becomes confusing, is often people throw a lot of mathematics in. So I don't want to worry too much about the detail of the maths, but just the impact. So regression, if we go to a simple regression, you have X inputs. So you have, think of as like columns of data, what column 1, column 2, columns to up how many ever columns you've got, or variables or features. And then what you do is you have some kind of coefficient or weight that you multiply the value in that column by. And eventually this gives you an equation which comes out with your predicted Y value. So your loss, as I said before, it's really just a simple comparison of what's the real value to your predicted value. And that's how you calculate the performance of your model, as you saw from your last model. But now with this penalty, what it does is it adds this extra component. So in this case, what it's doing is it's summing up all the weights or coefficients that are applied in this regression model, and then adding that to your score. So the impact that has is the more coefficients you add here, or more X values you have, this score gets bigger, i.e. worse. Or the higher each individual coefficients are, again, makes the model score worse. So every time you're adding more into your model, it will increase this penalty, therefore you'll get a worse loss score. So that means it really has to improve the error to outweigh the penalty. So hopefully that's relatively clear.
Got it, yeah. So just very crudely, you're saying add in an extra cost in addition to the error that just counts how many variables you have, basically.
Yeah, absolutely. Now, there's one component that so you can control how heavy that penalty or how heavy that extra cost is, and that's called the lambda function, the lambda value here. I'll come into that into a little bit and show some examples. But effectively, in this example, you're adding up all these different weights. So the more weights, the higher weights, the worse score it's going to get. So that, I think, in the orange here is the really key aspect of that. We mentioned there's two types, lasso and ridge, right at the start. And they're very like the previous example where you had L1, which is mean absolute error, and L2, which means square error for your model error. It's actually the same thing for lasso and ridge. They can be called L1 and L2. So lasso has a regularization penalty that just uses the absolute values for your weights and sums them up. The difference is ridge does the square. So that's the key difference between the two is one uses the square of the weights, and the other one just uses the absolute values.
So that's a little mysterious, but I think you're going to explain really what the difference is between these, right?
Yeah, so that's where I think if you read on this online, it starts to get confusing, because you get a lot of mathematical and diagrams, and it's good to understand that, but I think the more important thing for me was just to understand the impact rather than worrying about the mathematics. So I sort of summarized this into, because which would you use? And I'll show a little demo after this of doing a real regression model and how it impacted my analysis. But for me, the key difference is that because of the different calculation, lasso reduces the weights of coefficients to 0. That means effectively it's time multiplying some of your features or variables by 0, i.e. they're gone. They have no impact on your regression. They've effectively been removed from your model. So lasso is really good at actually removing variables from your model. So it really simplifies it down. Ridge is different. It doesn't remove things from your model. It doesn't remove variables, features. What it does is it reduces the coefficients that those features are multiplied by. So it's actually almost making the coefficients more regular, if you like, which is the only way I can see how the word regularized.
I see. Got it.
Because instead of having coefficients that go minus 200, 10, 1,000, it will make them all sort of come towards more common values that are closer together.
So Colin, I want to make sure you've got time for your video, but for your demo rather, but just very quickly, why use lasso versus, lasso seems kind of obvious, right? It is variable reduction, which we all believe is a good thing, but why use ridge at all in that case? What's the difference? Yeah, so lasso is good because it does feature selection and it literally takes out values. The big problem with lasso and where ridge comes in, if you are have lots of correlated features, for instance, or you know you've got value in features, or even you don't know but there's value in the features in there, lasso can kick them all out, whereas ridge will retain every feature. So sometimes I think you could combine them both, where you could have lasso actually doing some feature selection and reducing the equation down to a point, and then using ridge to then bring the coefficients down to be more regular. So in a way, ridge doesn't really reduce complexity. It just reduces the coefficients to not be so extreme. Can that help with collinearity, for example? Yeah, absolutely. So, I mean, ridge can address things like collinearity. I can't even say that. It's a bad word for me to pick. But yeah, so the ridge is because it can work with features that are correlated and sort of bring down the value of those. So that's a great point to bring in the demo, because I'll show you where lasso actually has a negative impact because of that correlation between variables. Okay, go ahead. So I'm going to jump out to this example here. So what I've got here is this is using our typical data science tool. And the example I've got is we've got a lot of data from our Formula One simulator. And what we're doing is we're using regression to predict people's lap times as they race. So we've got a lot of inputs. So if I just click on a node, it'll show you all the inputs. So we've got a lot of variables. You can see just how many there are. There's about 130. But that's a lot to deal with. So I've got 3 regressions. Standard regression, I've got one running lasso and one running ridge. And what I've done is built those models, and then I've got this holdout test set to see how good they are. So if you look at the actual equation of the regression, it comes out, the standard one, you can see it uses all these different coefficients. And it comes out with an R squared of 0.5. If I use lasso, you notice a huge difference. Just notice how many zeros there are. Cool. So you can see there's very few variables left. Ridge, on the other hand, it has all the coefficients and variables still, but the values are much. Is there a way we can visualize this? Yes, absolutely. And one of the interesting things as well is that the R squared versus the test set, the linear regression had the highest R squared from training, but it actually gets the worst R squared overall from the test set. And that's an indication it's overfit. So lasso and ridge. And you notice the lasso and ridge perform almost the same. So let me just show you the outputs of this. So the standard regression here is all these variables, and these bars are the coefficient. So you can see it goes from negative 100, 200 to 100. Lasso, all of these have a value. Even the ones close to 0 will have a value. So even if it's just minus 0.01.
But what you'll see in lasso is there actually is only very few here and here, maybe only 7 variables that still have a value, i.e. all the other parameters are no longer used. Ridge is again different. It's reduced these, so notice it's from -140 to 20. So it's taken down the big coefficients, made them more common. So you can really see the difference. But what if we're talking about correlation? So this is because it's data from a car. You might say all 4 wheels data will be correlated. So what this is really interesting here. We've got 2 attributes of the wheels. So this is the front wheel and the rear wheel. What happens in lasso is it's only kept the front wheel and it's kicked out all the rear wheel.
That's probably too aggressive, right? Probably too much.
Yeah. Whereas Ridge has kept them both in, it's just reduced the impact of the relay.
Oh, that's great. Oh, that's a great illustration.
Yeah. So that's really important because a car, your rear wheel might touch the grass and your other wheels are on the tarmac, in which case the rear wheel is really important in whether you're going to slow down or skid. So this is an example where lasso is probably too aggressive, where I might use Ridge.
Cool. That's much clearer, Colin.
Yeah, so let me just go back to the slides. So hopefully that was a nice demo. The one thing we didn't really touch on too much was lambda, but in these things you can tweak lambda, and that increases the impact because lambda is multiplied by, multiplies your penalty. So the higher lambda, the more aggressive the lasso or regression impact will have.
So how do you find the optimal value? Is that one of these cross-validation options now?
Yeah, there's no right way to do it or wrong way to do it. It is really exploration. It's like it is a hyperparameter. You can use cross-validation, you can explore it. It'll be different per data set. You know, I use 0.03 in here, but even if you put it up to 5 or down to 0.1, you will get varying results of what comes out. And sometimes it'll flip which model's the best. So it's really another part that data scientists need to explore per data set.
Right.
Yeah, so that example of exploring models, last talk we talked, from Peter talked about the ways to pick the best model. We used R-square here very quickly to settle, but there's lots of different ways, and putting it into your domain is really important. So it's just to say that we've got more content on the example I was showing around lap times in an F1 simulator that people can look up on our community and YouTube channel as well.
Great, definitely check that out. Yes, I can imagine Peter will be saying to us now, use AIC or adjusted R-squared. Yes. I can hear it. Hey, are there other model types where you can apply this method besides regressions?
Yeah, so regression I picked because you know, it's been an interesting experiment, and it's very common, and I think it's the easier one to explain. But every single model can use regularization, because if you think about it, you can describe or penalize overly complex models in very different ways. If you've got a tree, you could come up with some way to penalize how many nodes that tree has, how many branches, or how many trees in total in an ensemble. In a neural network, it's often called weighted decay. So it starts to penalize how many neurons or how complex that neural net is. The key thing is, if you can take out 60% of the parts of your model and it still performs the same, then why wouldn't you? You know, you've got a much easier to explain model and interrogate and use.
Cool. Okay, thanks, Colin. That was so clear, and that example really brought it to life for me. Thanks very much for talking to us today. That's really great. Ninad, any final questions or wrap up?
Yeah, means other than lasso and ridge, Colin, are there any other options?
Yeah, so lasso and ridge are the most famous. There's actually a whole suite of options that people I don't tend to see often being used, but if you go into the more mathematical aspects, there are lots of ways of creating a penalty factor. But one of the most interesting is called elastic net. And what that does is it combines lasso and ridge together. So it adds both penalties onto that equation to work out model performance. And then you get a balance between the two. So it's trying to get the best of both worlds. So if there was one that somebody would explore, I would suggest trying elastic net, because it should, there's some people who argue it's better than lasso and ridge always, but I like to keep an open mind. But that's a really interesting one because it takes the best parts of both methods and combines them.
Cool. Thanks so much, Colin.
Okay. So as I mentioned, guys, next session is on July 15th. It's on time series. So I hope to see every one of you. And thank you very much for joining today. Thank you, Colin and Stephen. Have a great
Thanks a lot. Bye.
rest of your day.
Thank you very much. Cheers. Bye.